Executing multiple operations at the exact same time is a standard efficiency goal in software design. You want the system to do more work in less time. But the moment those parallel paths intersect on a single piece of shared data, the system breaks down. When multiple independent execution paths attempt to modify the exact same memory address simultaneously, the system does not elegantly merge their instructions. Operations that appear instantaneous to the programmer at the code level take time at the hardware level. Mid-execution, they are silently interrupted and overwritten by the system. This hardware-level interruption results in silent data corruption, lost updates, and completely unpredictable program states. Reliable performance depends on protecting shared mutable state from the entropy of overlapping execution. To build those protections, we have to define exactly how tasks are executing. Parallelism is literal, physical, simultaneous execution, where different tasks run on multiple separate CPU cores at the exact same time. Concurrency is different. Concurrency is the interleaving of multiple tasks in overlapping time periods, managed entirely by an unpredictable operating system scheduler, rapidly switching context on a single core. In environments like the Java virtual machine, these concurrent tasks are packaged and executed as threads. Look at this snapshot of a standard operating system's performance monitor. The CPU is actively juggling nearly 5,000 background threads continuously, just to maintain a baseline environment. Because threads are this lightweight and numerous, developers must assume the execution order is inherently non-deterministic. The schedule is entirely out of your control. To isolate where data corruption happens, we have to map the process architecture. A process is the primary unit of program execution, and it maintains its own highly isolated private memory space. Threads exist within that single process boundary, acting as lightweight subunits. They share resources with unrestricted access to the process's code, data heap, and file handles. However, every thread maintains its own exclusive registers and call stack. Those remain entirely private. This architectural division explains why local variables inside a method, which live on the thread's private stack, are thread-safe. Meanwhile, class-level variables sitting on the shared heap create significant risk. Sharing the heap while isolating the stack allows rapid communication between threads. It also creates the exact mechanism for a race condition. Let's examine a race condition using a basic action, incrementing a counter with C++. To the C++ CPU, C++ isn't atomic. It requires 3 distinct steps. Thread A reads the current value from memory, retrieving a 0. Before it can add, the thread schedule ruthlessly pauses thread A. Thread B bypasses it, executing all 3 steps, reading the 0, adding 1, and writing the 1 back to memory. A microsecond later, thread A wakes back up, unaware of what just happened. It executes its addition step based on stale read data, calculating 0 plus 1. Thread A then writes its result back to memory, overwriting the address with its own value of 1. This is a lost update. Thread B's work was entirely erased without throwing a single error. Because the language does not guarantee atomicity by default, the data silently corrupts. Even if a thread completes a write operation without interruption, there is a secondary hazard built into modern hardware. Individual CPU cores cache data locally for speed. They do not write data immediately back to the main RAM on every step. Because of this caching, thread B might read a stale value from the main memory, completely blind to the fact that thread A just updated that same variable in its own local CPU cache. To solve this memory visibility crisis, the Java memory model introduces a formal requirement, the happens before relationship. Happens before is a strict contractual guarantee that all memory writes by one specific operation will be forcefully flushed and made visible to subsequent operations. You trigger this guarantee primarily through manual synchronization and the acquisition of locks. Achieving thread safety means actively fighting both the OS scheduler's interleaving and the hardware's caching. You must use explicit commands to force order. The canonical test case for coordinating shared state is the producer-consumer problem. One thread generates data, and another thread processes it. A common incorrect approach is a spin loop, or busy waiting, where the consumer continuously runs an empty while loop checking if the data is ready. Busy waiting is wasteful. It monopolizes a CPU core doing zero productive work. And without synchronization, there is no happens before guarantee. The consumer might never see the producer's update due to memory caching. The correct solution is the guarded block pattern, utilizing Java's intrinsic locks, also called monitor locks. When the consumer thread calls wait inside a synchronized block, it voluntarily drops the lock and suspends itself. It consumes 0 CPU cycles while resting. Once the producer thread generates the data, it calls notify all. This awakes the suspended threads, safely transferring control and the lock back to the consumer. Intrinsic locks solve both hazards simultaneously. They enforce mutual exclusion to prevent lost updates, and they establish a happens-before relationship to guarantee memory visibility. Implementing synchronization locks fixes race conditions, but it introduces an entirely new systemic failure: liveness problems. Liveness measures an application's ability to actually make forward progress in a timely manner. The most severe liveness failure is a deadlock. It occurs when synchronization locks are applied incorrectly across multiple threads. Look at this bank transfer involving 2 nested locks. Thread 1 successfully locks account A. Simultaneously, Thread 2 locks account B. System paralysis hits when Thread 1 attempts to lock account B, while Thread 2 attempts to lock account A. Neither thread will release its initial lock until its overall task is finished. Both threads are permanently frozen, waiting on the other for eternity. Preventing deadlocks requires strict architectural discipline. You must ensure that all threads across the entire application acquire nested locks in the exact same global order. Before we close, we need to address a frequent technical trap. A common error is initiating a new thread by calling the run method directly instead of start. Calling run directly does not create a new thread. It simply executes the code synchronously on the current active thread, entirely defeating the purpose of your concurrent architecture. The start method is the only way to instruct the JVM to actually allocate a new, independent call stack and hand it over to the thread scheduler. Concurrency is highly effective, allowing you to maximize hardware utilization and hide latency by running overlapping tasks. The cost of that efficiency is exposing shared mutable state to non-atomic CPU operations and memory visibility lags. Engineers must architect synchronization mechanisms to counter this, balancing strict locks against the hazards of deadlocks. Mastering that exact balance is what separates junior coders from systems engineers.